specimen preparation, the significance of specimen preparation, I have explained it, that it is very important in every material and for each and every technique. It is basically the specimen preparation which decides about the nature, about the composition, about the phase constitution, which phases are present in a specific material. These all depend upon the specimen preparation. That are you skilled enough to prepare the required specimen for that particular technique? Secondly, is the specimen representative of what you are studying? Just like if you take a piece from somewhere and it is not representative of that material, as I told you, in minerals we commonly have different materials within a mine, and the mine may be containing 95%, for example, diamond, and 5% will be quartz. But if you pick the sample from the quartz region, it is not representative of the 95%. So technically people question that is your sample really representative of that particular material? And that is why people sequentially study the transformation of phases with temperature and take sample at each step, that what is happening to the material with temperature. Secondly, they are not confining or limiting their study to a specific sample, but the representative study which reflects the reality of this material is that you select sample randomly from different parts of the same material, right? And again, when you describe those results, you don't say that this material contains these phases or the chemical composition is this. No, you truly say, carefully say that I selected samples from here, here, and here. And the microscope told me this, and that for each sample. So you are not blaming or promising anything on yourself. But what you see, then you compare your result with other people, and there you discuss and analyze what you have done and what other people have done. So you are reporting from the machine which tells you something. If you see that this room is made of potassium or sodium aluminosilicate, this is a wrong statement. But if you say that I took a sample from that part of the wall, I took one from the ceiling, one from this wall, and the machine found this phase in this area, this phase in this area, and this phase in this area. This means that the room contains these phases. And if another person comes and selects a sample from anywhere else, then he or she may tell something else. And that is why you are not promising yourself, you are not claiming yourself that this is this. No, this sample collected from this region, when was put in the microscope, it revealed this phase in this material. The grain size was like this, the morphology was like this, the phase constitution was this, right? So you are referring to the specimen. You are not referring to the mine or to the mountain from where you took the sample. So in general, we can divide specimen into two types: self-supporting specimens and specimen resting on a support grid, or thin washer. Washer is also, as I told you in previous lectures, it is a ring like this. So this is the washer in the sample is fitted or fixed or stuck over that washer. So the washer thickness must not be that much to affect the position. So it must be very, very thin, right? And in self-supporting specimen, you cut a thin, small slice from the main sample, then cut that into discs, 3 millimeter diameter discs. As I told you, you do it with slow saw, diamond saw. You cut the sample, the slice from the main material. Then you grind it up to 100 micrometer thickness, slightly above or below. That doesn't mean that it is a Quranic word that it must be 100, right? It can be thinner or a little bit thicker, but if you don't follow that particular instruction, then when you do ultrasonic drilling is also a sensitive technique, and if instead of 100 micron you are cutting 200 micron, then you are damaging the equipment. That is why people specify that these rules, these instructions must be followed. Then pre-thinning of disc. Pre-thinning of disc means, as I told you, that you put the sample on the dimpler and a wheel is running like this. A wheel is like this. The sample is rotating like this. So when the wheel is running like this and the sample is rotating like this, then it creates a dimple like this. So you dimple this area. So if it was 100 micron from here to here, if it was like this. So if this is 100 micrometer, then this is about 25 micrometer or less. And I have told you that if it is more than 25 micrometer, it takes very long with argon ion thinning. And the next step is final thinning, electropolishing, and iron milling and coating. So this pre-thinning, they mean that if the sample is like this, then you can grind it a little bit from here as well if the sample is thick, right? So that you are left with very little area here, about 25 micron or less, and they are referring to that as pre-thinning. The dimpling, as I told you, that the sample is like this and the wheel is like this. It is rotating in the middle, and the wheel, it is usually a stainless steel wheel. Stainless steel wheel, and you put a very soft cloth over it. It is one side is sticky. So when you pick the wheel like this, if this is the wheel, then you cover it with that cloth, sticky cloth, and then you put a little bit diamond paste. So the cloth very finely rotates here like this. The sample is rotating, the wheel is moving like this, but the sample is horizontally in rotation. So when it is in rotation like this, the middle is, in the middle they create a dip. But that is cloth, and it is not because of the mechanical strength of the cloth, but because of the diamond. It rubs paste of diamond with the sample, and very softly it is grinding the middle of the sample. Because if it is a wheel, not cloth, then it will scratch the sample and there is a chance that it will break. And the wheel cannot cut it. It is the diamond paste which is polishing it. And another important thing is that if you are using cloth, very fine cloth, and the diamond paste is softly grinding the middle of the sample, then the sample appears as finely polished as well. So there will be no rough lines or scratches of the wheel on in the dimpled area, because a scratch can damage the sample very badly. And secondly, the sample will appear very ugly when you put it in the machine. So that is why the cloth and the diamond paste are very, very important there. After that, you put the sample in the iron beam thinner, and the iron beam thinner is something like this. Uh, it is a cylindrical shape. This is with grooves, and here you have something like this, and put a plate with the 3 millimeter hole in the middle. Here you leave a 3 millimeter hole in the middle in the sample holder. You put the sample here, it is a little bit deep. Here, you put the sample here and you put that top plate on it, and there are screws here. And you fix these screws so the sample is gripped like here. And this is fitted into the machine. It has grooves here at the bottom. When it is fitted into the machine, then it rotates with the machine. And the argon iron beam are coming. If it is only top-sided, then the argon iron beams are coming like this. And if it is double-sided, then also in this direction, and they are hitting the sample and skipping. The eyes are skipping. Skipping in Pashto means sati, licking the organ iron beam, skipping the surface. So they are just hitting the surface and move like this. This is skipping the surface like this, and in this way you thin the middle of the sample in a very controlled manner. After each hour, 2 hours, 3 hours, depending on the sample of the thickness of the sample, you come and look into the sample. Usually there is a fine small microscope there fitted over the sample holder, and you look into it that how much thin it is. If the thickness in the middle decreases and you see light there, that yes, now it is transmitting the light, then instead of this angle, you decrease the beam angle, like instead of this, you decrease the like this, so that it just skip the surface finely. It's not going deep into the sample. It's not hitting deep the sample. Similarly here, and it just skips the surface. If the beam is like this, it is hitting the sample in such an angle that the beam will go deeper and deeper. But if it is like this, then it is not going deeper. So by changing the angle of the beam, you are decreasing the extent of thinning, but you are actually polishing the surface like this and like this. Polishing is this, grinding is this, right? So decreasing the beam angle, you are polishing the surface, and this polishing increases the thin area. If the angle is higher, then it is only thinning the center, and the center will be much thinner in comparison to the periphery. But if you use the lower angle, then it is homogeneously thinning and it gives you relatively more thin area on the sample, and this is the self-supporting sample. You are adding nothing to the sample. You are not supporting the sample with any sort of ring or washer or grid. It is purely your sample, and that is used in the specimen resting on a support grid or a thin washer. I haven't used those techniques which are self-support. Some of them I have used, but not all of them. So they are electropolishing, ultramicrotomy, grinding and crushing, and lithography, replication and extraction, cleaving, and chemical etching. All these techniques means that you are making use of some chemistry of the solvents, and at the same time you are using a mechanical process which are thinning or slicing and different things are occurring. Now look, if you are cutting a sample mechanically, it makes the cross section you are making very rough. But if I use a chemical which is dissolving the material as the salt is passed on it, then instead of mechanical pressure, the cutting occurs because of the chemical, and that is a soft way of cutting. So when you soften the cutting or polishing or grinding, what happens? The material is not damaged.